So there's one last thing that we need to talk about for this section, and that is a new test. We've been learning about a couple different tests for determining convergence or divergence. Actually, in this section here, we got one test, the alternating series test, and then we got the tool of looking to see if the series is absolutely convergent by taking a look at the series form and the magnitude of the terms. And if it is absolutely convergent, then it is convergent. So we have that in our tool chest here. But now, the last test is sort of a sledgehammer. It can be used quite a bit, and it has a lot of force behind it, hence the sledgehammer analogy. But it also can do some damage, or tell us things. I'm going to rephrase that. Or it cannot be. Maybe sometimes it's not useful. So you'll see in a moment. So let me scroll up here and let you see what the ratio test is. All right, so there's three parts to it. I don't know if all of them fit on the screen. There we go. The first part says if the limit as n approaches infinity. Now, be careful with the structure here. So what are we taking the limit of? We have the absolute value of something. Okay, so we need an absolute value in here. And if you look at the something, the numerator is the n plus first term, and the denominator is the nth term. So we're just looking at the ratio of consecutive terms, okay? An n plus first term divided by an nth term. And if that limit of that magnitude, that ratio goes to some number L, and L happens to be less than 1, then the series A sub n is going to be absolutely convergent. That's nice because absolute convergence means convergent, so and not conditionally so, and therefore it tells us quite a bit. Now in part B, if we take a look at the same limit of that ratio, when we get a number L that's bigger than 1, or that limit goes off to infinity, then the series is going to be divergent. And then lastly, in part C here, if that limit equals 1, the ratio test fails, and we have to apply a different test. So there are, some very useful times we're going to use this. It becomes especially useful when we have factorials involved, and you'll see that in some of the examples we will do in a minute. But nonetheless, we're going to be using this one a lot when we get into the next section, when we start talking about power series, and we want to know when power series converge. And so the ratio test is going to be our primary tool for doing that. But it doesn't work 100% of the time, as part C tells us. It fails when that limit becomes 1. And so we do have to be careful. We have to make sure that we apply it properly, and we pay attention to what we get, and we don't include 1 as a possible point of convergence or even divergence. We just don't know. When the limit is 1, we have more work to do. We'll talk about that in just a moment. One thing I do want to kind of relate is to this to you through is for some understanding is a geometric series. If you look at this relationship here, it should conjure up a little bit of what was happening when we were taking a look at a geometric series. If you think about a geometric series, we know a geometric series converges if the common ratio has a magnitude less than 1. Well, that's kind of what the ratio test is telling us, at least by analogy. What we're doing is we're taking the limit of a ratio. Okay, it's not a common ratio because we're going to apply this to series that are not geometric. But we're taking a ratio of consecutive terms, and if you actually had a geometric series and you took the ratio of consecutive terms, that is the common ratio. The n plus first term divided by the nth term gives you a common ratio. And we're taking a look at the magnitude here. So if we took the magnitude of the common ratio, and that's less than 1, this series converges. Well, that's what this is telling us here. If we take the limit of the magnitude of the consecutive terms and we do get a number that's less than 1, then we know the series is going to converge. And the nice thing is we get absolute convergence. Similarly, if we take that limit of that ratio and we get a number that's bigger than 1, then we know the series will diverge. Or if the limit goes off to infinity, the series will diverge. Now, the geometric series, when the magnitude is equal to 1, then those series diverge. If the common ratio is 1, or for a geometric series, or the common ratio is -1 for a geometric series, in both of those cases, the series will diverge. But here for the ratio test, we don't know because we're not taking, it's not geometric in general. And so we have to look at those occurrences when the limit is one, especially to see what's going on using a different test. And again, you'll see some example of this later. So to help commit this to memory, if you can, make the analogy to the ratio test, then I'm sorry, not the ratio. This is the ratio test to a geometric series, and the ratio test will be easier to remember and hopefully will make more sense to you. Let's look at some examples. Before I get to those examples, let me make a quick comment here. In our algorithm for thinking through how to prove whether a series is convergent or divergent, which I'll go through in a minute, I want you to think about where the ratio test fits into this. In general, you need to figure out if a series converges or diverges by any means within your arsenal. The algorithm that I have you think through tends to be the most systematic way to go through everything you're supposed to know and come to a conclusion efficiently. Now, if you see a pattern right away and you know, oh, with this pattern, I know it's this, I know I need to use this tool, then you can jump right to that tool. But the algorithm is a guide for those who tend to get stuck right away and need a process to think through. So the way I teach it, the first thing we try to do is identify a certain type. And if the series is a certain type, then we apply the methods for that type. If it's geometric, we know when a geometric series converges. If it's alternating or P series, whatever it is, we apply the rules for that particular series. Then we get into the nth term test for divergence. If the nth term does not go to zero, then the series will diverge. If the nth term does go to zero, then we have more work to do. Then we get into a branching here. If the series has terms that are all positive, then we have at our disposal the integral test, the basic comparison test, and the limit comparison test, and we can use any one of those. The ratio test also works in that category on that branch. Okay, if the terms are all positive, you could still use the ratio test. And then if the terms are not all positive, the other direction, then we don't have much at our disposal. If they aren't all positive, we have the alternating series test, but that goes up with the certain types. If you notice it's alternating, then you could use the alternating series test as one of your types back in step one. But down here, if the terms are not always positive, what do you have at your disposal? Well, you have absolute convergence. You could take a look at the series form of the magnitudes and see if those terms or that series converges. And if so, then the original series does as well. Or the ratio test. Now, so the ratio test is on both branches of that split from positive term only and non-positive term series. So you can use the ratio test in either case. It's indiscriminate as to whether the terms are all positive or not. So you have it as your disposal. So that's our algorithm right now. And then at the bottom, after all of those things don't work, then you have the definition always to use at the very end. Let's see. Example number 5, does the series converge? And we have these 3 examples here. I would like you to think through the algorithm a little bit, and start by identifying types and if possible, look at the nth term test and then go from there. That doesn't mean I want you to try all the other tests. I'm not asking you to try the integral test or the basic comparison, limit comparison test, unless you see a way that you may be able to accomplish showing whether or not the series converges or diverges using that tool. But we are going to practice, or I'm going to practice the ratio test in the work that I'm going to do. So I recommend that you try first going through the algorithm a little bit just to get, train your brain to think through systematically the process, and then try the ratio test on this. Try to set it up yourself, and then take a look at what I do. That way you understand you'll have an understanding of how well you comprehended what I was talking about or not. All right. Anyways, let me get to it. So if you want to do those things, pause the video now. Now for part A, again, I'm going to use the ratio test. So the ratio test says we need to look at the limit of the absolute value of the n plus first term. Now that means I got to change anything that in any place where there's an n, I'm going to replace that n with n plus 1. So it's going to be 2 to the power of n plus 1 divided by the quantity n plus 1 factorial. You need parentheses there. And then we got to divide by the nth term. That's the actual term that we see here, 2 to the n over n factorial. Okay. Going forward after this example, you won't see me write it this way over and over again. I'm going to jump to the next step because it's mostly just algebraic laziness. We know that when we divide fractions, we're going to multiply by the reciprocal. So I'm not going to write this fraction as the first step every time. I'm going to jump into the next step where we, again, multiply by the reciprocal as we are very familiar with. So this becomes this expression here. And the nice thing is we have some algebra that we can cancel some things out with, like 2 to the n and 2 to the n plus 1. We can divide those. We can cancel. Think about what's left. Hopefully you realize that there's a 2 that's left up here. If you're not sure why there's a 2 left, remember if we're dividing two expressions with the same base, which is what we're doing here in this expression, we subtract the exponents. So n plus 1 minus n is just 1, so we're left with 2 to the first power, or just 2. Now, believe it or not, there's some things that cancel between the n factorial and the n plus 1 factorial. And to illustrate this, let me go do a little bit of side work here because this is going to be helpful for everyone to see. Let's think about how we would expand n plus 1 factorial. Well, normally when we write like 5 factorial, it's 5 times 4 times 3 times 2 times 1. So let's do that here. So this is going to be n plus 1 times, well, I got to subtract 1, so that's going to be times n, and then I got to subtract 1 again, so it's going to be n minus 1, and I got to keep subtracting 1, and that's going to happen all the way down until I get to 1, like this. So what is this? Well, let me point something out down here with the, sorry, I'm trying to change the color of my pen. Here we go. 5 factorial is 5 times all of this stuff here, but hopefully you recognize that this is just 4 factorial. So 5 factorial is really 5 times 4 factorial. We have that pattern happening here. The part that I've just denoted, that's n times n minus 1 times n minus 2, all the way down to 1. That's n factorial. And so we have n plus 1 times n factorial. That's another way of writing what n plus 1 factorial is. Well, that's nice because I have I have n factorial here, and I know n factorial is a factor of all of this, and when I cancel those out, I'm left with an n plus 1 here in the denominator. So let's go slowly. Let's proceed slowly here, and let's see what we got. So this becomes the limit as n approaches infinity of the absolute value of 2 divided by n plus 1. The absolute value really isn't doing anything for us here. I could have dropped it, earlier in this expression because the terms are all positive anyways, and the absolute value of a positive number is exactly the same thing, same number. But I'm just leaving it there. Later on, you're going to want to keep it there. We're dealing with power series, the next section. And we're going to want to keep it there as long as we need to for reasons we'll talk about later. But nonetheless, as n goes to infinity, 2 divided by n plus 1, when n is getting larger and larger, is just going to get smaller and smaller, get closer and closer to 0. And the nice thing about 0, for our purposes here, that's less than 1. So what does that tell us? By the ratio test, as we saw above, that tells us that the series is going to be absolutely convergent. So therefore, by the ratio test, the series from n equals 0 to infinity of 2 to the n over n factorial is absolutely convergent. So now that if you were struggling with the ratio test before, now that you've seen me work out an example, it would be a good idea to go try the others on your own just to see how well you understood what I just talked about. And again, I don't know what just happened here. Undo that. Okay. Computer issues again. I was moving this over because you could see just the 0 less than, but you couldn't see the less than 1 the way I had the screen. And so it was bothering me a little bit. Anyways. All right, so here's part B. Hopefully you've had a chance to try it on your own. Take the limit again as n approaches infinity. Now we need the n plus first term, so I'm going to put n plus 1 squared, 2 to the n plus 1 plus 1, which is going to be n plus 2, all divided by 3 to the n plus 1. Now I have to divide that by the nth term, which means multiplying by the reciprocal of the nth term. So as I said, I'm going to not write the ratio first. I'm going to go right into the algebraic next step. All right, so now from here, again, we're going to have some things that cancel. And so really simply, 3 to the n and 3 to the n plus 1 is going to cancel, leaving a 3 here. 2 to the n plus 1 and 2 to the n plus 2 are going to cancel, leaving a 2 here in the numerator. And something's wrong. I know what's wrong. I forgot a part of the expression. So let me fix that. This should have an n squared here. So hopefully you caught my mistake before I did, and that's good. But at least I caught it. All right. Let's rewrite what's left. Okay, so I have 2 times the quantity n plus 1, and that's squared, left in the numerator after everything cancels. And I have 3n squared in the denominator. And I still got the absolute value. Again, for this example, all the terms are positive, so the absolute value has no effect. And we'll reflect that in just a moment. Anyway, let's keep going. If I take the limit, letting n go to infinity, the nice thing here is that my highest power of x in the numerator, when I apply the exponent here, is going to be n squared. And my highest power in the denominator is also n squared. And so when the highest powers are the same as n goes to infinity, then the answer is just the ratio of the coefficients. And the coefficient in the numerator is going to be a 2, and in the denominator is 3. So the answer to this limit is going to be 2/3. If you want, you could expand the n plus 1 squared, distribute the 2, divide by the highest power of n from the denominator, and get the same answer. I'm just being a little more lazy, if you will, efficient, however you want to call it. 2/3 is less than 1, which tells us that this series is going to converge absolutely. Okay. This series converges absolutely. All right, so one more to do. I'm changing the starting n value here for part C to 1, so we don't have 0 to the 0 in the numerator. It wasn't quite paying enough attention to my notes, so that's okay. This is going to be n to the n, and this is going to be n factorial. Starting at 1 doesn't affect anything that we're doing anyway. Once again, I hope that you have taken the opportunity to try to work this out without seeing my work first. If not, I mean, it's up to you. It's your choice, but I think it's just better for you if you do the work before you see me do the work. All right, so this is what we end up with using the ratio test, or setting up the ratio test with the n plus first term divided by the nth term. All right, so what cancels in this mess? Well, as we saw earlier, n factorial and n plus 1 factorial reduced down to just an n plus 1 here. Nothing cancels along these two terms, the n to the n and the n plus 1 to n plus 1. I can't cancel anything here, but I can cancel this with one of these and leaving just an n here. Because the numerator, I mean, this was n plus 1 times itself, n plus 1 times, and so I'm just going to divide or take out one of that product, cancel it with the one down here, and be left with just n of those. So that's the algebra thus far. Let's see where this goes. So now I'm left with, I'm going to go slowly here. So n plus 1 to the n over n to the n. Maybe you see how you can rewrite that, and if not, that's okay. Over time, you've got to sharpen those algebraic skills. So I got to give you some hints about what you have and what you don't have. This algebraically can be rewritten as n plus 1 over n, all raised to the nth power, which can be further simplified or rewritten as, not really simplified, but just rewritten as, I could separate this fraction, n plus 1 over n, as to n over n plus 1 over n. So this becomes n over n is just 1 plus 1 over n raised to the nth power, as n goes to infinity. You should recognize this number. It's come up before, came up, when we learned L'Hopital's rule in the AB class, and we haven't reviewed that much. And I think it came up in some other notes that we did not too long ago. But nonetheless, hopefully you recognize that this limit as n approaches infinity is e, and you could show that. I'm not going to take the time to go through in much detail here, but you can set y equal to 1 plus 1 over n to the n, and then take the natural log of y and get n here like this, and then take the limit of this expression and then rewrite it algebraically, do some L'Hopital's rule, and then undo the natural log, and eventually you'll get e if you do it right. If you need some help with that, let me know. I can send another video some other time to help with that. So the key thing here is that e is greater than 1, and so since the limit of that expression is greater than 1 by the ratio test, this series is divergent. All right, so the ratio test, again, is going to be a heavy hitter for us, so you're going to want to make sure you kind of have it down. But you're going to get plenty of more practice when we move into the next topic. And so that's why you only get 3 examples here, because there's plenty more to come. Go study.